better focus on the macroscopic patterns. So we first tried to find out what is influencing the crack growth in a material, what is influencing the crack, how does a crack find its way through a material. And there are some mechanisms, some toughening mechanisms in each material, which are in general look like this here. For example, there is a front wake mechanisms. A crack is coming, for example, to a particle and does need to find a way around the particle or through the particle or something. It loses energy by developing through the material. That every of these processes, every single particle absorbs energy from the crack. So it's toughening the material. Toughness is the resistance against the crack to growth in a material. So we do find this in our composites because they have the fillers inside. We also have it in glass ceramics because they have crystals inside the material, but the mechanisms are somehow comparable. And we do have these front wakes in zirconia, where the particles in the vicinity of a crack, they start changing their shape and their volume in order to absorb the energy of a crack and reduce the velocity. We also have some bridging mechanisms. So once a crack, for example, if you have a fiber reinforced material, then a crack needs to spend the energy in order to pass the fibers, whether to crack the fibers or to go around the fibers. And this is done in a lot of industrial applications, from bicycles to fiber reinforced materials. And there were some trials also in dentistry using fibers in resin composites in order to increase the toughness. And of course, with a certain grain structure, metals do have a grain structure, and oxide ceramics, you could also suppress and deviate a crack through the material. And then we find some indication on some macroscopic indication on our composite for kind of crack branching. Crack branching is if you have a single crack and there's a certain plane, a particle coming, a certain second plane opening, and you have two cracks. All these processes, they absorb the energy from the crack and reduce the energy. So we found this kind of second plane, this one here, for example, where the material loses the energy. And we also went deeper into the microstructure, seeing is there any indication if the crack is stopped exactly at the interface to a particle, at the silanization. Does it somehow exhibit the surface of the particle itself, or does it go around inside the matrix, or where does a crack proceed through a material? And you see here the nanoparticles as you have seen it in the other presentation. So we went deeper into this structure, and you don't see any exposed particles. So actually, there is a quite good silanization of the particles in the matrix. So the weakest plane, the weakest point in the material is the matrix itself. The crack goes around the particles and finds its way. And if we go further, we see there is one of these particles which is totally covered with a resin matrix. And then, from our knowledge, we know there are this kind of appearance here, but there are also different materials with pre-polymerized fillers, for example, or exposed filler particles. And we went to those particles, like this material here. You see the exposed particles, and you could question, well, there's a worse silanization of the particles. The interface is weak, and the crack finds a nice way to open the crack planes exactly at the interface. And then we went also here in the vicinity of the particles. You see this here, or better in this field. But these sharp crack planes you see here, the exposed particles, they turn out to be covered as well by resin composite. Here you see the resin composite. So it's somehow necessary to look deep in the microstructure to find out the related mechanisms in terms of strength and fatigue. We found different appearances. If you see here, for example, these three materials with a different fractographic appearance, then we see exposed, or let's say you see the particles at least, and you don't see the particles. There are more and more materials coming to the market which use prepolymerized fillers. And these prepolymerized fillers, they have, you see here, you can read it, 40 microns is the bar. So they are huge compared to nanofillers in a different materials. So we need to also to focus in this certain field of different filler configurations in a material, and we can easily compare the appearance at a fractographic plane. This is just to show you that there are differences. We are at the very beginning of this field, so we try to start developing research in this field, but we see differences, and we see there is an indication also on resin composite fracture surfaces. And well, the final goal, of course, would be to get clinical indications, clinical evidence, to get clinical failures by impressions or by particles released from a fracture, to observe them clinically. What is the reason for failure, in order to state, is a fast fracture, or is a slow fracture, is it a fatigue fracture, or like that. But you can do that in principle if you find the particles which have fit in here, and you can see the fracture surface, and then you can analyze the fracture surface. But this is the topic of another talk today. Coming back to the very beginning, what does it tell us? The fatigue, the strength of a material, is that somehow related to a clinical outcome? It's difficult. These questions are always coming up, and there is no direct influence, because it's a number of parameters coming together, making the clinical success and the lifetime. But what we have seen, these are clinical studies on resin composites, which we did in our university. And we have seen some of the materials are really good clinically, and some of them are not. There are reasons. Well, of course, in the posterior region, if we use a glass ionomer material, it's quite predictable that the strength level is very low. But there are also other materials which somehow do not fulfill the criteria for clinical studies. And then we could somehow state, well, there is a certain limit where we come together from the clinical side and from the lab side, saying, well, at least we need 25 to 30 megapascal in the lab for a material in order to say, well, this is a clinical relevant fatigue limit for a material. And with this, I thank you for your attention, and I would like to say happy birthday to Christa. I think he's going to be 80 years old tomorrow, or the day after. So he's very resistant against fatigue. So, well, thanks.